Today we begin with Chapter 5 of the book of Prigogine, the Phenomenological Laws, Interference of Irreversible Processes. Section 5.1, the domain of validity of the phenomenological laws, chemical reactions near equilibrium. So in this section we are going to determine the domain of validity of the linear phenomenological laws. Remember that the phenomenological laws are the laws which relate the flows with the forces. And in this case we're considering only linear relations between the flows and the forces. In reality, the system may express non-linear relations between flows and forces. But for this section, we're only considering the domain of validity of the linear phenomenological laws. So the example we're going to give today is of a transport process, the flow of heat in a continuous system. So remember that the entropy production is just the flow times the force. And in this case, for the flow of heat in one direction, Wx represents the flow of heat, and the force is the gradient of the temperature in the x direction over t squared. And that, by the local formulation of the second law of thermodynamics, has to be positive definite. And that is equation 1. So if we assume a linear relation between the flow of heat in the x direction and the force, which is the gradient of temperature in the x direction over t squared, then the phenomenological relation for a linear case, we have Wx is equal to minus L, L is some constant, over t squared, times the gradient of the temperature in the x direction. This is equation 2. And this is of course nothing more than Fourier's law with the heat conductivity, lambda, equal to minus L over t squared, the temperature squared. Therefore, the domain of validity of the phenomenological law, equation 2, is the same as the validity of Fourier's law for heat flow. Now, Fourier's law of heat flow is valid if the relative variation of the temperature is small within the length of a mean free path. That means the distance, the average distance between collisions of the particles in the system, which we define as phi, phi being the mean free path. So the validity of Fourier's law requires that phi over t times the gradient of the temperature in the x direction is much less than 1. If this is satisfied, where phi is the mean free path, then Fourier's law is valid, and then we can assume that we have a linear relation between the flow, which is the heat flow, and the force, which is the gradient of the temperature in the x direction over t squared. In fact, Fourier's law is satisfied in most cases, particularly when the density of the material is large, so that we have a large number of interactions. So the mean free path, phi, is small. The only place where it really doesn't apply is in vacuum or in outer space, where the density is very small and there are very few collisions with respect to the gradient of the temperature. Let's consider now a different irreversible process, which is the chemical reaction. So we consider that we have a single chemical reaction occurring in the system, and for that system, the phenomenological relation is the flow, the rate of the reaction, is equal to some constant L times the force, which is just the affinity over the temperature, equation 5. Now, since the entropy production is just the flow times the force, where the flow is equation 5, and the force, remember, is A over T, so the entropy production then becomes L is equal to A over T squared. So let's consider the accuracy of this linear phenomenological law, equation 5, relating the flow, which is the rate of the reaction, or the velocity of the reaction, to the force, which is the affinity over the temperature, Let's consider it for a particular reaction, in this case for the production of hydrochloric acid. So if we have a molecule of hydrogen plus a molecule of iodide, that gives us 2 molecules of hydrogen iodide. Or another name for hydrogen iodide is hydrochloric acid. Now remember, the affinity, which is related to the force for the reaction, is just minus the sum of the stoichiometric coefficients times the chemical potentials. And remember that the stoichiometric coefficients are negative on the left-hand side and positive on the right-hand side. So the affinity for this reaction 7 becomes A is equal to mu H2, which is the chemical potential of hydrogen, plus mu I2, the chemical potential of iodide, minus 2 mu Hi, which is the chemical potential of hydrochloric acid. Now remember that the chemical potential for an ideal mixture, or a mixture of perfect gases, is just given by equation 3.24 or equation 3.25. If we neglect the dependence on pressure, then the chemical potential is just eta, where eta is some function of the temperature plus RT, R the universal gas constant, times T the temperature, times the logarithm of the concentration of the component gamma in this case, which would be, in our particular case, either hydrogen or iodide. C gamma, in fact, are the molar concentrations, or the moles per liter, for example, of a substance, gamma. Now remember, in chapter 3, equation 3.41 and equation 3.25, we define the equilibrium constant in the form of equation 10, where R, the universal gas constant, times the temperature, times the log of this equilibrium constant, which is a function of temperature, is equal to minus the sum of the stoichiometric coefficients times this function eta of temperature, which defines part of the chemical potential for element gamma in the system. So remembering again that the affinity is just minus sum over all the components in the system of the stoichiometric coefficient, the component, times the chemical potential of the component, and using equation 9 for the chemical potential, we get an equation of the form equation 11. If we now substitute equation 10 for the equilibrium constant as a function of temperature, K at T, into this equation 11, we get that the affinity is equal to the universal gas constant R times the temperature times the logarithm of the equilibrium constant as a function of temperature over the molar concentrations of the components, all the components in the system, raised to their stoichiometric coefficients. So then, for our particular case of the production of hydrochloric acid from iodide and hydrogen, we can write the affinity then in this form, equation 13. Now, from the kinetic theory of gases, the kinetic expression for the reaction rate, V, rate of the reaction, is just the rate in the forward direction minus the rate in the backward direction. And from this kinetic theory of gases, this is just equal to some rate constant K in the forward direction times the concentration of iodide, the molar concentration of iodide, times the molar concentration of hydrogen, minus the rate constant for the backward reaction times the concentration, the molar concentration of hydrochloric acid raised to the second power. And it's raised to the second power because that is the stoichiometric coefficient. So by rearranging terms, we can write that in the following form: just the rate constant in the forward direction times the concentration of iodide times the concentration of hydrogen times 1 minus the relative rates in the backward to the forward direction times the concentration squared of hydrogen iodide over the concentration of iodide times the concentration of hydrogen, which is the final term of equation 14. Now the ratio of the kinetic constants in the forward direction over the kinetic constant for the backward direction is just equal to the equilibrium constant K, which can be a function of temperature. So remember that we always have forward and backward reactions occurring, whether we are out of equilibrium or in equilibrium. When we are in equilibrium, the rate constant for the forward reactions is equal to the rate constant for the backward reactions. So therefore, the equilibrium constant in equilibrium becomes equal to 1. So substituting the equilibrium constant in equation 14 and then comparing with equation 13 gives the following result: that the rate of the reaction is just equal to the rate in the forward direction times 1 minus the exponential of minus A, that's the affinity, over RT. It's equation 15. You can check this out yourself doing the algebra, just substituting the equilibrium constant for the rate constant in the backward direction over the rate constant in the forward direction, and then using equation 13. So we get an equation, which is equation 15, for the net velocity of the reaction, which is related to the velocity in the forward direction times this function, which is just 1 minus the exponential minus the affinity over RT. So now let's take a particular case or a particular condition that we are close to equilibrium. Remember that at equilibrium the affinity goes to 0. There is no force for the reaction. So if we're close to equilibrium, we can write A over RT is much less than 1. Equation 16. And for this case that we are close to equilibrium, then equation 15 reduces to this equation 17, which is just that the net velocity of the reaction is equal to the velocity in the forward direction near equilibrium, okay, or at equilibrium, since we're assuming that we are very close to equilibrium, over R, the universal gas constant, times the affinity over the temperature. So this P with superindice E, which refers to equilibrium, is the value of the partial rate of the velocity at equilibrium. Remember, we have a rate in the forward direction and a rate in the backward direction. And at equilibrium, these two are equal, and so therefore the affinity is equal to 0, as we stated before. So therefore, going back to equation 5, which related flow, which is the rate of reaction to the force, which was A over T for the chemical reaction, we can see from equation 17 that the constant L, this phenomenological relation, in the case that we are close to equilibrium, is just equal to minus the velocity at equilibrium in the forward direction over the universal gas constant, R, equation 18. So therefore, close to equilibrium, the value of this phenomenological coefficient L only depends on the value of the velocity of the reaction in the forward direction at equilibrium, which of course is also equal to the velocity in the backward direction at equilibrium. That is in fact what defines equilibrium, that these two rates of reaction are equal in the forward and backward direction. So that was the case for the situation where we are close to equilibrium, where we had the affinity over RT being much less than 1. Now let's consider the other extreme case in which the affinity is very large, so that A over RT goes to infinity. So therefore, from equation 13, this implies that the concentration of iodide, the concentration of hydrogen over concentration of hydrogen iodide squared goes to infinity, or in other words, that concentration of HI goes to 0. And this, for a closed system, corresponds to the initial stage of the reaction, in which we don't have any product. Concentration of hydrochloric acid is equal to 0. We're at the beginning stages of the reaction. So therefore, at the beginning stages, the net velocity of the reaction is given essentially by the rate of the reaction, or the velocity of the reaction in the forward direction, equation 21. So in this case, when the affinity is very large at the beginning of the reaction, we in fact find that the velocity, or the rate of the reaction, becomes a constant value, which is the value of the reaction in the forward direction. So in this case, the flow is not proportional to the force, the case of very large affinity. We have then a nonlinear relation between flows and forces. And the entropy production, for the case that the affinity is very large, is just this velocity, the rate of the reaction, times the affinity over the temperature, which just becomes some constant, which is the rate in the forward direction, over, times the affinity over the temperature. And so we have this entropy production becoming a linear function of the affinity. Remember that in the case that we were close to equilibrium, the entropy production becomes a function of A over T to the power 2 squared. So there's a difference depending on the value of the affinity. So therefore, for chemical reactions, in contrast to simple transport processes, like the transport of heat or the transport of material, linear relations between rates and affinities are not always justified, and it is necessary to take into account the nonlinear relations, like equation 21. So in equation 21 we have the velocity, or the rate of reaction, being constant value, which is the rate of reaction in the forward direction. So we have seen that for the case of a chemical reaction occurring close to equilibrium, then we do have a linear phenomenological law between the rate of the reaction and the force, which is just the affinity over the temperature. But if we have a very large affinity, for example at the beginning of the reaction, then we no longer have this linear phenomenological law. What we have is that the rate, the reaction, becomes a constant value. So it's not proportional to the force, which is the affinity over the temperature. However, if the affinity of a chemical reaction is large, it may be possible to divide the reaction into a number of more elementary reactions, each having its own particular affinity, being small. So in the end we can justify having linear phenomenological laws for each one of these individual reactions in the overall reaction, where the affinity is large. So let's consider the reaction M going to F. and assume that this proceeds through a number of individual steps. First, for example, M going to N, which is reaction 1, and then N going to O, reaction 2, and then so on, down to P going to F, which is reaction R. So the overall affinity of M going to F may be large, but the individual affinities of each of these intermediate steps may be small. So the entropy production due to these successive reactions then is just the sum of all the affinities of the temperature times the velocities or the rates of the reactions. This is equation 29. So now if the intermediate components N, O, and so on up to P are unstable, that means that they transform into another product, then we will eventually arrive at a steady state in which all the velocities of all these individual reactions will be equal to each other, and so we can assign them all a single velocity v. And so that after a short time the entropy production is just A times V over T, where A in this case then becomes the sum over all of these individual reactions of the affinities assigned to each of these individual reactions. A then is the macroscopic affinity. So therefore if each of these individual affinities over RT is much less than 1, then we are still in the domain of the linear phenomenological laws, which are the laws between the reaction rates and the affinities, even if the total affinity is much greater than 1. The total affinity over RT is much greater than 1. And this in fact appears to be the case for many biological reactions which occur in steps. So we still have linear relations between the flows and forces for many biological reactions, even though the overall affinity may be very much greater than 1. And this is due to the fact that the overall chemical reaction is in fact many individual reactions in sequence, all of which have an affinity over the gas constant times the temperature much less than 1.